Alright, so we're about to start with data link layer today. So far we've done from the transport layer. We were able to discuss that the transport layers have more to do with reliable or unreliable, data transfer or information transfer. We're able to sample some of the protocols on the transport layer that either supports reliable delivery of data or unreliable delivery of data, being the TCP and the UDP. Then we discussed the connection-oriented networking and the connectionless oriented networking. I want to believe that you still remember each and every one of those concepts, because often and often these things will repeat them or make use of them, in order to be able to understand newer concepts as we're going further. Then from transport layer, we discussed about network layer, and we mentioned that particularly the network layer, the networking device that resides on this layer or functions primarily, or its main duty is to assist with the responsibilities at the network layer, is the router. Router is the only networking device that resides or functions at the network layer. We discussed a lot about that. Be sure to revise what we did if you happen to have forgotten any of them. So we mentioned that routers make use of routing tables to be able to identify networks, because a router's business is only with network. So basically what it does is, once it receives a packet from a particular host that is supposed to, that the information that is to be sent is destined for, let's say, a network of 192. Let me use Notepad to be. So let's say from my computer, I'm about to send you a message, and then in the course of packaging everything, the information that I'm about to send, I specify that this particular message I'm about to send is to be sent to the person whose IP address is 192.168.1.3. Okay, now this is the destination. Let's say this is the destination address, IP address, and let's say the source IP address is, let's say, 192.5. blah blah blah. Anything, just type in anything. So once this information with this IP address reaches the router now will know that this is the source IP address where this is where this information is coming from, and this is the person that this information is heading to. So all the router has to do is, because these numbers are basically identifying the network with which this host is residing in. So basically all the router needs to do is, look at this networks specifically and then compare it with its routing table. See if there is a match. When it finds a match, or when it finds a configuration, it will now decide, which of the exit interfaces or exit ports is it going to send this information out from. So a router's main duty or main work is basically to try to locate where it can, which door, which exit it can use to be able to reach a particular network where a message is sent or destined to. We discussed that in our previous class. Then we also discussed the data link. After the network layer. After the network layer, we're supposed to discuss the data link layer. So that's where we are going to start with today. Now, as I mentioned, the data link layer is the next layer close to the physical layer. Now, when you read this particular section, you'll see what the data link is all about. It says the data link layer provides the physical transmission of the data and handles error notification, network topology, and flow control. Meaning that it is at this data link layer, that is, and mind you, data link layer, that is where switch, hub, and bridges, this is where they function. So at the data link layer, the networking devices that you have that are operating at this layer are the switches, the hubs, and the bridges. Bridges are more or less extinct, so basically hubs and switches. So once the router now eventually keeps routing the network, the message through the different routers or hop counts, as you can remember, when it eventually gets to the network where that has the router that has the network attached to it. Now the switch would the router will basically send the information to a switch, a layer 2 device, being a switch or a hub that is connected to it. So it is at that layer 2 device, a switch or a route or a hub, that the messages are now delivered to the proper device. They will now locate the proper phone, proper laptop, or proper desktop computer that the message was intended to. Okay, was intended for or something. So that is the switch's work basically. So the way it does that, or it's able to detect the particular system that was supposed to receive that message, it's through the hardware address. Okay, through the hardware address. Now the switch also helps to translate messages from network layer into bits for the physical layer to transmit. So in the event that the data still needs to get to another router, still needs to get to other routers or other devices in order to still reach the last terminal host that is destined for, it is the data link layer, it is the switch or the hub that will convert the messages, as this place is saying, into bits. Take note of this. So now convert into bits. Remember, bits are a series of zeros and ones. That's your binary. So the data link layer or the switch will now convert the whole big message into bits of 0 and 1s that will be sent to the physical layer, which is the layer 1, to be transmitted either through wire, because at the physical layer you have physical layer is more or less a link, the link between one network and another, and the link can either be through fiber optic cables, can be through the normal internet cables that you know, can be through wireless. So the data link layer device will now convert the messages into bits that will now be transferred through the appropriate physical link connection or something. Now the data link layer formats the messages, the pieces. Okay, yeah, so take note, at the data link layer, this is the format in which the message is saved as. When it gets to the data link layer, messages are saved as a frame, as a data frame. When it gets to the network layer, messages are saved as a packet. Okay, they are converted at each stage, because you remember we mentioned something about wrapping. You remember when we said something about DHL, when you're about to send a parcel from here, from Abuja here, to somebody in Enugu through DHL. When it gets to each of their offices, they will wrap it on something that will let them know, okay, this is our office, where it is going from Ogun office to Lagos office, from Lagos office to Sokoto office, till eventually gets to the final destination and final depot. As it's going through each of those offices, they will tear out the former office's wrapper and then wrap their own to identify the location where it is going. So that's basically what the layers do. So at the data link layer, information or messages are saved as a data frame, and as it's saved as a data frame, it will customize it with its own header or its own custom information that has to do basically with the hardware destination and source address. So by the time I'm about to send the information, this will, by the time we go deeper, we will see how this encapsulation processes takes place. But just have it in mind, or bear it in mind, that as the message is passing from one let's say switch to the other, there are some hardware destination and source address that are added or removed to the messages at each layer. Now this added information forms a sort of capsule that surrounds the original message. It's form of something like a wrapper that will now surround the main message, that each layer 2 device receiving the new message will first of all look at that header and know what to do with that particular message. So let's see. So basically, okay, we'll look at this a little bit later as we go down the book, because the data link layer, it comprises of two different major protocols. That is the LLC, or is divided into two sub layers. Let me put it that way. It's divided into two sub layers: the LLC, logical link control, and the media access control, which is the MAC address. Okay, so now here is trying to help you know that you remember that routers don't care about where a particular host is located. The routers don't know anything about the destination host, the main destination host. All they care about, routers, all they care about or are concerned about are the destination networks. Okay, the network, how it's going to move from one network to the other, from one network to the other, until it gets to the final network where the destination host is. It doesn't, the router's concern is not to send the message to the particular destination host. No, rather router's role or work is to be able to route or move that network, that message from the source network to eventually to the network that the destination host is inside, is staying in. So once it gets to the network that the destination host is staying in, it is now the work of the switch or the hub on the data link layer to identify which of the hosts is actually supposed to receive that message. So here is now helping us to appreciate that in order for a host to send packets to an individual host on a local network, okay, each time a packet is sent between routers, as the packet is moving from router to router, it will be framed with a control information at the data link layer. Take note, in order for assuming these are the two routers, okay, in the network, in order for this guy to successfully move from here to this other router, it will go through, because remember I mentioned that in the OSI model you have the 7 different layers. Layers 4 to 7 that are on the top. They are concerned more about, they are more about what the message would be like, it will be sent to, what it's looking like. From 4 to 7 they are determined by the host, but from 1 to 3, okay, from 1 to 3, or more or less 1 to 4, should I include 1 to 3 are involved. Layers 1 to 3 are involved in order for a packet to leave one networking device to the other networking device, regardless of what kind of networking device is. So if this is a switch and this is a router, before this message leaves this switch into this router, it will pass through layers 1, 2, 3. Before this message from a hub gets to a router or a switch or whatever, or a host, it will move from layer 1 to layer 3. So what here is now saying is that each time a packet is sent between routers, it is framed with control information at data link layer, meaning that before this guy moves from here to here, even though there are two routers, it has gone through a layer 2 activity before it moves from one router to another. Remember we mentioned that the router is a layer 3 device specifically for networking. A switch is a layer 2 device specifically to identify the destination host. But before any of these guys send any message, some of these things usually happen. So don't worry if it's a bit confusing, it'll get more clearer as we move upper and upper. So as information is moved from one router to the other, the original packet is left intact. That is the original message. If the message I was sending to you, from me to you, is I am coming, that I am coming message, text message, remains intact. But the things that will be padded or added to that message in order for it to move from network to network to network, to be able to finally identify you or locate that is you, Daniel, that I'm sending this message to, that is what it means that it's continually framed with control information that will assist the networking device to transmit that message from one place to another. Please, if there is anything you don't understand, by the time you finish watching the video, feel free to let me know so that I'll record something else on a particular one you don't understand. So this framing of packet continues for each hop count until the packet is finally delivered to the correct receiving host. So packets are never altered along the route. The main message will never be altered. The I am coming message I'm sending to you will never be altered. Rather, what will be altered will be the control information, maybe like destination address, source address, destination hardware address, source hardware address. These are all the informations that will be framed and reframed, so that, because imagine if these are 3 routers, and I need to, okay, maybe this is you, and you are connected. This network that you are connected to is connected to this router, and me, this is my own router, and the network I am residing is on this end. If me I'm on this end of the network, I want to send a message to you on this end of the network. It means my message will have to get to this router, from this router pass to this router, from this router pass to this router, from this router then pass to you that is residing there. Okay, so as the message is going from here to here, so those are the different types of information that will be altering in the course of the message moving from router to router in order to finally get to you. That is what this is trying to explain when it says that the packet itself never gets altered along the route. It's only encapsulated, it's wrapped with new. So the main data itself is never changed, or it's never altered. But the only thing that changes is the control informations that are padded to the main data in order to be able to move it from one router to the other router till eventually it gets to the router that has the destination network connected to the router. So it's very essential that this information, you have it close to heart. So the data link layer now, as this page is helping us to appreciate, is now divided into 2 sub-layers. The first sub-layer is the media access control, 802.3. Take note of these code numbers, 802.3. So this is the layer where the hardware address of the destination hosts or the source hosts is relevant or is made use of. Okay, so here says physical addressing is defined here, as well as logical topologies. What's a logical topology? Is a signal path through a physical topology. We'll get to see this eventually later, but by this the logical topology is simply referring to the network topology, the hierarchy of the network, how the network is, the LAN network is strategized. Take note, at the media layer, at the data link layer, you are now on a LAN network. Okay, at the media, as in the switch functions within a LAN, whereas the router functions within a WAN, wide area network. So physical addressing is defined here at the media access control sub-layer, where you can have many of these other things happening at this layer. They could be line discipline, error notification, take note, not correction, ordered delivery of frames, and an optional flow control. Okay, so these are some of the things that function at this media access control layer. But take note, most importantly, that this is where physical addressing of the hardware device, the MAC address or the hardware address, 2 of them are the mean one and same thing. That is where it operates. Now at the LLC layer, being the logical link control, this is the layer that is responsible for identifying network layer protocols and then encapsulating it, and then encapsulating them. An LLC header tells the data link layer what to do with a packet once a frame is received. Take note, we mentioned that this packet and frame things, these are the encapsulations, the wrappers that are used on a data packet as it is reaching any of these devices. I will mention that when we discuss that OSI model, we mentioned that, as you being the sender, okay, the message will move from the application layer gradually down to the physical layer to go from top to bottom. But when the message is received by a receiver, it will go from the bottom back to the top. So it will pass that message from the bottom layer by layer till it gets to the top layer. If the device is actually the intended destination host, then the message that was sent as it is being received, it will go up to the 7th layer. But if it is not the intended receiver, the final destination host, let's say the message is now forwarded from you on the network to a switch or to a router, before getting to, as it is moving from a switch to a router, the highest it can go is layer 3. When it gets to the layer 2 and sees that it's not the device, it sends it to the layer 3. The layer 3 networking being a networking device, being a router, will now know, okay, I'm not the receiver, I'm not the one whose this thing is responsible for, or this message is intended to. It will now forward it to another layer 3 device. So once it forwards it to another layer 3 device, it now goes from, as it's forwarding it, take note, it is now the sender. Let me take time and explain this thing better. As it is going from top to bottom, it is passing through each of the 7 layers to transmit, as in from the original source host, to transmit the message. Now, as I'm transmitting the message, as it's going out now, it has gone from layer 7 to layer 1. Then it goes out through the wire to the router. The router receives the information and knows that, okay, this information is meant for Daniel on this end of the network. I am simply a conduit pipe or a transmitter, somebody to help to forward the message from this network to this network. That is what the router knows. So the router will know that by the time it looks at the network, the informations, so it now reaches that layer 3. It sees that, okay, this is not my network. The network is this guy's network, and to get to this network, I must pass it to this other router. So as it's forwarding it to this other router, it will now, the message will now be re-encapsulated with this one as a source. We'll get to all those one later, but it will now go from that layer 3 it was received, layer 3, to now go back to layer 2, layer 1, out to this other router. This router receives that layer 1, layer 2, layer 3, and at layer 3 determines that, okay, this message is not intended for me, it's intended for this guy who is on this network. How do I get to this network? I get to this network through this other router. It determines that information. Then it now tries to forward the message to this router. Now layer 3, layer 2, layer 1, the message goes out, gets to this router. This router receives it, layer 1, layer 2, layer 3. It looks at the destination, it sees that the message is intended for this guy, and this guy is inside this network. You now say, okay, good. It now forwards it out, layer 3, layer 2, layer 1, forwards the message out to this final guy, assuming this is you, Daniel, on the network. So once your own device now receives the message, it will now, from layer 1, layer 2, layer 3, okay, I am the correct person and the destination host, and I'm the person who this message was sent to. Okay, layer 4, layer 5, layer 6, layer 7. That's usually how it goes. So it's at that LLC layer that this place is saying that this layer is responsible for identifying the network protocols and then encapsulating them. The LLC header will tell the data link layer what to do with a packet once a frame is received. It works like this. A host will receive a frame and look in the LLC header to find out where the packet is destined, say the IP protocol at the network layer. The LLC can now provide flow control and sequencing of control bits. Let me talk on what this simply means. As this guy is receiving the message, okay, looks in the as this router is receiving the message, it looks at the data link layer. It looks at the LLC information that was encapsulated by this guy before he sent it out, and he sees that, okay, this message, once it's being received, it's to be handled, because a single router can run different types of routing protocols. Only this guy can handle, remember all those routing protocols we looked at, we said that usually generates routing tables. We have RIP, we have OSPF, we have EIGRP, and the rest of them. So a single router can handle maybe all of these routing protocols. There's a way it's usually configured. So if the LLC receives, and that's a protocol, those are protocols on the layer 3, okay, protocols that function on the layer 3, that's the routing protocols, RIP, EIGRP, OSPF, I think there's ISIS or ISPS, something like that. So assuming a single router is running all the 4 of those protocols, all 4 of those protocols cannot handle a single packet. One of them will handle a single packet at a time. So it is at that LLC section of the data link layer that when it receives a packet, that the receiver will now determine, okay, this packet that I've received is intended for the IP protocol on layer 3. Remember I said as the receiver is receiving it is going from layer 1, layer 2, and layer 3. So at that layer 2, and as it's passing through, it's passing it to the proper protocols on those different layers that will take the next action. So if it gets to layer 1, maybe layer 1, it will handle to pass it to MSC. MSC will look at the hardware address and the source destination address and the the source hardware address and the destination hardware address. This guy takes care of it. Then maybe it will now send it to the LLC. LLC will now look at, okay, which of the routing protocols on the layer 3 should I send this packet to handle it? Is it RIP? Is it OSPF? Is it AIGRP? All those informations that are to be determined to know which of the layer 3 protocols the layer 2 will forward the packets to. That is what LLC handles or takes care of. So that's what this guy helps to do, basically. Please, anything you don't understand, just write some comments and then let me know so that I'll be able to produce more videos on it. And this one is still talking about layer 2 switching. Just read all these ones and take them to heart. Latency is the time measured from when a frame enters a port to the time it exits the port. So this is very key. Latency is the time from which a frame enters, from when this guy receives a frame from its layer 1 and sends it out from the layer 3. The amount of time duration for each of the protocols to look and do all they need to do, wrap and unwrap and wrap the information as it is about to go out. That is what latency is all about. So bridges and switches, they read each frame as it passes through the network. Okay, so that's what it's basically. All those LLC information, reading the packets, removing the former source and destination hardware addresses, putting a new one, encapsulation. That is what bridges and switches do as the packet is going through each of them. So it says the layer 2 device, let's say a switch or a hop at the data link layer, will put the source hardware address in a filter table and keep track of which port the frame was received on. So what that means is that, assuming this is the host, okay, and you're about to send me a message. I'm here on this side of the network, and this is you on this side of the network. And assuming these are switches, this time around, don't view them as routers. These are switches because we are looking at layer 2. Layer 2 has to do with switches or hops. Assuming this is a switch here now, what that means is, as this guy is sending a message through here, as in he wants to send a message out to this guy and it's coming to this switch port. The switch now, once the message lands on the switch will now record inside its filter table that, okay, this particular host, this is your MAC address, your hardware address, so, and this hardware address is accessible through port 1. Take note, remember that a switch has numerous ports. So that anytime that somebody wants to send a message to a hardware address that belongs to you, when it gets to this guy will look at its filter table and say, do I have a record of this so MAC address? And it will see, okay, yes, I have this so hardware address and it's accessible through port 1. So it will not need to do anything. It will just forward your message through port 1 to you because it has already captured and registered you as belonging to port 1. That is what this statement is saying, that the layer 2 device puts the source hardware address in a filter table and keeps track of which port on it the frame was received on. Okay, so this information is what will help the switch or hub to determine the location of the specific sending device. So anytime you're sending message, if you were not captured and registered, the switch will capture your IP, your hardware address, and the port in which you're connected to, and register it. So anytime somebody sends you a message, you just simply look at its table, locate your hardware address and the port in which you are accessible through. So basically that is it. So primarily layer 3 machines such as routers, they need to locate networks. So routers worry about how to locate networks. So their own routing table that they have, everything they do is about how to locate network, a network that the host is staying inside. It's just like me trying to send a DHL to the person and trying to locate the community where I am staying. So the router is just to try to find the particular network where the host is staying inside. Whereas the layer 2 device is to try and actually identify the particular host in which the message is intended to, because it is the layer 3 device, the router works, it deals with networks. Okay, that's why it belongs to a wide area network, because there are so many routers. So it deals with locating the networks, whereas the switch, which is a layer 2 device, it works on the layer 2, which is the data link layer, which has to do with locating the main host itself. So the switch or the layer 2 device, it functions on a LAN network, usually on a LAN network, which is the next, the next step before you eventually reach the final destination recipients. So after a filter table is built on a layer 2 device, it will forward frames only to the segment where the destination hardware address is located. What I just mentioned, as you are sending, if the switch does not have any entry of the ports in which you are sending message, it will record it. So any other time it wants to send message to you, it will just simply send it through that particular port to get to you. So that is a switch work. Okay, so these are typical examples. So this is a typical switch now. You can see it has port 1, 2, 3, 4. So as this guy is sending a message, if there is no record of this guy's hardware address, it will just capture his hardware address and note that he sent an information through port 1. When this guy sends to capture its hardware address, I know that this guy is accessible through port 2. This hub is accessible through port 3. This guy is accessible through port 4. So it knows all those information. Now it now knows that even these guys are accessible through, to access them, it will have to go through port 3. If you want to access this other guy, it will have to go through port 4. The switch dynamically gets all those information, records or saves them, and then keeps them, so that anytime this guy wants to send a message to him, when the message he is sending gets to this switch, the switch will now know that the doorway through which to get to this guy is through port 1. So it will just forward the message to port 1. If he's sending to this guy, by the time the message gets here, to know that the doorway to this guy is through port 2. He won't send it through port 1. It will rather send it through port 2. So all the devices have their particular. That's why they say that switches usually they help to break up the collision domain and ensure that you don't have network congestion. Alright, these ones are informations that you are already conversant with. Alright, now let me see how I'll be able to explain this in a way you'll be able to understand the binary to decimal and hexadecimal conversion, because this thing is very important. Very, very, very important. It will come a long way when you are trying to calculate how to apportion IP addresses to a particular network. So pay attention to this very well. Now, the simplest way I can break this down to you is that, as you know, networks are usually transferred in the form of bytes, okay? And bytes usually are a combination of 8 different bits. Okay, a byte is 8 bits, or you can have 4 bits, which is a nibble. So informations are sent out in bits or in bytes. So in bytes now, you now to compose of each byte is made up of 8 bits, smaller like that. So just picture it this way. Usually many of these things, they work with a byte, which means a combination of 8 different digit placements. You have 8 different digit placements. Each of them, to know their equivalent decimal values, you will have to multiply them by 2. So for this first one, this one is usually, just assume it's usually taken as 1. This is the starting point. That is the 1. Then 1 times 2, this gives you 2, which is the second value of the second position. The 2 times 2 will give you 4. 4 times 2 will give you 8. Be following along with this guy. 8 times 2 will give you 16. 16 times 2 will give you 32. 32 times 2 will give you 64. 64 times 2 will give you 128. So each of these bytes, each of these bits in this byte, the byte is the whole of this. The bit is each and every one of this. Each and every one of them are individual bits. So each of these individual bits, if their value is 1, then this is their corresponding decimal equivalent. Please, I want you to take note of this. So for this 1, if you have this byte now, the first one here, its corresponding decimal equivalent is 1. The second one, its corresponding decimal equivalent is 2. For this is 4, 8, 16, 32, 64, and 128. So if you have a byte like this, if you're given a byte like this, as you can see, this is 1, 2, 3, 4, 5, 8 different bits making up 1 byte. To know the decimal equivalent of, okay, for example, this byte now, its decimal equivalent is adding each of these respective bit equivalent decimals to get 255. So the decimal equivalent of a byte, a binary byte, is 255. So if you have something like that for all of them being 1s, for this one now that you have a mixture of 0s and 1s, the ones that are 0s, you leave those ones out, because it's like saying these ones are 0 times whatever its value is. So the equivalent of this guy is, that this guy, ideally this bit position is supposed to be 1, but since it's 0, you keep it as 0. 0 plus this one is supposed to be 2. So that's 0 plus 2 plus this one's equivalent is 4 plus 4 plus this one is supposed to be 8, but since 0 is here, we keep it as 0. This one is supposed to be 16, and it's 16. It's equivalent. This one is supposed to be 32, but since 0 is here, you put it as 0. This is supposed to be 64, but since 0 is here, you put it as 0. This one is supposed to be 28. So at the end of the day, if you're to calculate the byte equivalent of this byte, it's going to be 128. So you take note of each of these values, they are 1s, they are corresponding decimal equivalent. 128 plus 16 plus 4 plus 2. 128 plus 16 plus 4 plus 2, and that is what you are seeing here. Which bits are on? The ones that are on are the ones that are 1s. The ones that are 0s are the bits that are off. So you add up all the ones that are 1s, and you have the equivalent, which is 150. So for this guy, this binary, this byte now, its equivalent, the decimal digit is 150. Look at this guy now, almost the same thing. This is supposed to be 1, but here is turned off, so this is 0. This is supposed to be 2, turned off, 0. This is supposed to be 4, which stands 4 times 2. This is supposed to be 8. 8 stands because it's here. This one is supposed to be 16, but it's 0, so we leave it at 0. This is supposed to be 32, which is 32. This is supposed to be 64, which is 64. This is supposed to be 128, but it's 0, so we leave it out. So at the end of the day, to get this guy's decimal equivalent is going to be 64 plus 32 plus 8 plus 4. That's what you're seeing here, and that will, by the time you add this, you'll have an answer of 108. Please take note to so that is the same way in which all these other guys, their decimal value are gotten from each of the binary values. So for this guy, these are zeros, 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 zeros. So the only thing here is this last one, which is 128. That's why its equivalent value is 128. This one, all these are zeros. It's just this and this, which are 64 and 128. If you add those two, it gives you 192. So these numbers are what are usually deployed when you're looking at, we'll come to a particular section where we'll make use of this thing, and you'll see where it's very much very applicable. Okay, so that's for binary. Now when you come to hex, okay, hexadecimal, usually it's a combination of two binaries, and you know, of course, hexadecimal goes from 0 to 9 and then A to F. Okay, from 0 to 9, A to F. The A to F simply symbolizes 10, 11, 12, 13, 14, and 15. So you can be given a series of numbers and you're told to convert them into their corresponding hexadecimals, so or any converse way. The key to remembering that is that, first of all, you have to divide each of them into their corresponding nibbles. Nibbles is 4 bits. Okay, each of them 1, 2, 3, 4. 1, 2, 3, 4. Those are each of their responding nibbles. So you can see that, okay, for a hexadecimal value of 0, this is equivalent binary value, and this is from 0 to 9. For a hexadecimal value, this from 0 to 9 will be the same as its what's it called? Its hexadecimal, its decimal equivalent. Okay, and these are their equivalent binary values. For 6, to get 6, this is the binary equivalent of 6. How do we get it? Remember that this guy is supposed to be 0. I mean, it's supposed to be 1, but since he is 0, because first of all, it means if you convert this 6 into, to help you know how, if you convert this 6 into binary with your normal division, this is what you will get. Okay, so its equivalent is the same. That's why I said from 0 to, the numbers are just the same. Hexadecimal and decimal are the same. If you add this one now, this guy is supposed to be 2, this guy is supposed to be 4. 4 plus 2 gives you 6. If you remember what I just showed you now. Alright, now let me make it a bit clearer what I'm trying to explain. I know it might be a bit difficult to understand. Take for example, you're given a binary number like this, and you're told to find its equivalent hexadecimal and its equivalent binary decimal value. Okay, you're given a value in binary. This is binary number, and you're told, okay, find its equivalent hexadecimal value and decimal value. Okay, starting with the decimal value, you know that this is 1, this is supposed to be 1, this is supposed to be 2, but it's 0. So this is 1 plus 4 plus 16 plus 64. If you add all that, that gives you 85 as its decimal equivalent. Now, to get the hexadecimal equivalent, the rule is you divide this into 2. Okay, divide this binary into 2 nibbles. That's half, each of them containing 4 bits. Then you work on the 4 separately and the other 4 separately. So from this first side, this is supposed to be 1. This is supposed to be, this one is off. So this is 1 plus 4, which is 5. Now for this second section, this is 1 plus 4, which is 5. So you have 0 times, because this is what is used to indicate hexadecimal, 5, 5. That is what gives you the hexadecimal equivalent of this guy. Now look at this other example. Same thing implies. We're told to find the decimal equivalent of this guy. Okay, you know that these are zeros, so 1 and 2 are eliminated. So you start from 4, 8, 64, and 128. If you add all of that, it gives you 204, which is the binary, the decimal equivalent. Get its hexadecimal value. Divide this guy into 2. Okay, so you have 64 plus 128. 64 plus 128. So 0 times 64 plus 128 is what? Where is it? Okay, this one okay, converted to CC. Okay. That is A, B, C, 10, 11, 12. Sorry, I made a mistake. To get the decimal equivalent, the hexadecimal equivalent, remember I said you divide this into 2. And if you divide it into 2 now, this is one separate half, this is a separate half. Each of the separate halves, you start from 1, 2, 4, 8, like that. So for this first half, this is 0, so this is 4 and 8. 4 plus 8 is what? Is 12. And in hexadecimal, 12 is symbolized with letter C. Instead of just writing 12, you write letter C. So that's why this one, the same thing is here. 4 plus 8 for this second half. So for this guy now, the hexadecimal equivalent will be 0 times CC, which is what you will see here. For this other guy now, third example that will be traced it finally. Convert this guy to binary equivalents. What will it be? 1 plus 4 plus 16 plus 32 plus 128. That will give you equivalent of 181. Then divide this into 2. Divide this into 2. This is 1 plus 2 plus 8. 1 plus 2 is 3. 3 plus 8 is 11. That's A. So this one now is A. Let me check it well. This is 1, 2, 8. 8, 9, 10, 11. So 11 is B in hexadecimal. Now let's look at this other half. 1 for the second half, this is 1 plus 4, which is 5. So 0 times B5, that is what the answer will be in hexadecimal. I hope it's clear. If it's not clear, ask questions. So we now reach the physical layer. We're told that physical layer, basically its own responsibility is to handle the sending of the bits, each of these bits that we mentioned now, and bytes and whatever. Its own is just to send it. So either through wired cabling or any form of media transportation means, either wireless or through wire. Physical layer communicates directly with the various types of actual communication media. So it's the one that actually combines the two devices together. So different kinds of media represent these bit values in different ways. Some use audio tones, while others employ state transitions. Changes in voltage from high to low and low to high. That's what state transitions mean. As in what some devices use to transmit the data. Some will use audio tones, while some will use changes in voltage. This is where the electrical signals come to play in order to transmit a particular message. So specific protocols are needed for each type of media to describe the proper bit patterns to be used, how data is encoded into the media signals, and various qualities of the physical media's attachment interface. These ones are basically the wiring and everything. The physical layer specifies the electrical, mechanical, procedural, and functional requirements for activating, maintaining, and deactivating a physical link between end systems. Okay, this layer is also where you identify the interface between the DTE, data terminal equipment, and the data communication equipment. Okay, these are some terminologies you may still need to take note of. So multiple companies display blah 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 blah. DCE usually is the service provider. It's located at the service provider, while the DTE is the attached device. Service available for the DTE are most often used via a modem, channel service, data service unit, blah 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 blah. So the physical layers, connectors, and different physical topologies are defined by OSI standards, allowing blah 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 blah. Story. So this is a networking device that stays at the physical layer. So let me make a correction to what I've been saying. A hub is not at the data link layer, but it's at the physical layer. It's just more like the same form of connection that you have. So a hub is at physical layer because it's more like a hub is more like a multi-port repeater. It's more like a single wire that now, some wires that have different branches. Instead of now being, it's like extension socket from one fuse outlet. It will now provide 3, 4, 5, 6 different fuse outlets from that extension socket, all of which are drawing from the one single. That is what a hub is like. So an active hub does the same thing. So signal received from one port in a hub is regenerated and amplified and transmitted out of all the ports on the hub, just like an extension socket. The current it receives at the fuse and the mount will just be duplicated into the number of ports you have on the extension socket to send to other places. So hubs, like repeaters, they don't examine any of the traffic. They don't do anything with the packets as it enters. They just transmit it and retransmit it out to other parts of the physical media. So every device connected to a hub, they listen to a device transmission. That's why it belongs to one big collision domain. So the design really doesn't resemble a star, blah blah blah. Hubs and repeaters can be used to enlarge the area covered by a single LAN, but it's usually not recommended. So this is what a typical hub looks like. All the devices are in the same collision domain, same broadcast domain, and they share the same bandwidth. So Daniel, this is where we stop for today. So till I produce our next video. Bye bye.